All right, so second try here. I am recording this again because of the severe weather, UNL canceling stuff except for online and web conferencing stuff. Normally I would have live streamed this from home, but because of the rolling blackouts in Lincoln and Omaha, I cannot guarantee that it would work. So I'm going to go ahead and record this and provide it later, and provide an upload later. If you've got questions, please go ahead and go on Piazza and ask about it. I set up a thread for today's lectures where I'm going to put in links to today's lectures. You can go ahead and ask there, or you can just ask generally. So to continue where we left off last time, remember that we were working on this old homework here where we've got this isotope. An isotope has multiple pieces of data, an atomic number, name, a symbol, a half-life at which it decays. Strontium-90, for example, decays after about 28.9 years. So if you start out with 10 grams of strontium and then 28.9 years later, you would expect to have about 5 grams left over if you started out with an initial mass of 10 grams. That's ruled by this equation right here. Remember last time we went through the process of creating a class to represent an isotope, because the moment that you have more than one piece of data that represents something, the concept of something, that's a huge red flag that you should be taking those 5 pieces of data in this case, wrapping them up into one logical unit, in this case a class. That's part of good encapsulation. So we went through the process of designing this class. We've got an atomic number, element name, element symbol, etc. We've got a constructor here that we invoke from outside the class by using the new keyword, and we've created an instance. We've instantiated an instance of strontium-90 over here. And then we go over 29 years to just simulate the decay over 29 years. We did that by, well, we've got a bunch of getters here. We do have a setter here making our class mutable, that we can change it. We can set the mass. We're gonna redesign that today. But we also have a mutator method in that we've got this decay method. Because in our first attempt here, we were taking care of the decay outside the class. Basically that's bad encapsulation because it takes behavior that belongs inside the class. The class should be responsible for its own behavior. And we ripped it out and we located it over here. We put the equation and all of the logic for figuring out how much mass is left over here. Right? We don't want to do that. What we did is we took that and we put it into a method called decay. And now this method inside the class is responsible for figuring out how after 1 year or 2 year or half a year how much mass is remaining, and so that it resets its own mass, simulating that decay. And then it also reports to the calling function how much decay or how much mass is actually decayed over that time. Now, initially we designed this to be on the scale of years, and so we could, pass in 1 year like I did over here, but 1 year over here, or we could put 0.5, right? 6 months. But not all months are created equal, right? There are some months that have 31 days or 28 days, like this month. Sometimes during a leap year, this month has 29 days instead, right? So let's redesign this we thought about redesigning this method over here to be more abstract, to rely on the idea of a concept of time. Initially, what we did was we created this class because we want to model time, right? And so we came up with the idea of maybe modeling it with years or seconds or nanoseconds, right? If we did it with seconds, then that really pigeonholes us in we can't have fractions of seconds. So maybe we want to go to nanoseconds, right? Or picoseconds or whatever you want, right? Well, before we get ahead of ourselves here, what else might we want in this time class? We might want the functionality of given one time, 1 year and 3 months. We would also want to take and add 1 month. So we could subtract, right? We could say, given this period of time, 10 o'clock this morning, and this 3 o'clock this afternoon, how much time has passed between those two things? So that really actually highlights that we were going down the wrong path to begin with anyway. Time is a moment in time, right? And what we really wanted was we wanted duration, right? So we've got a lot of work to do here if we really want to do this. Let's back up. Now, like any good engineer, good engineers are lazy engineers. In that anytime they're approaching anytime you approach a problem, the first question you should ask yourself is this problem already solved? In other words, can you pull an off-the-shelf solution and apply it directly to this problem, or adapt it so that you can apply it to this problem, and you're done, right? You get to go home, right? Least amount of effort. That's the whole reason that we like automation. It's the whole reason we write programs to begin with, is so that we don't have to do this grunt work. It's why we like robotics, right? Because now all that grunt work is done by machines, and we're free to do higher level thinking or have more recreation time, right? So I'm going to go ahead and forget about time here. When you approach a problem, you should ask, is this problem already solved? When you write a function, you should ask yourself, is there a function that already does this for me? When you're designing a class, you should ask yourself, does this class already exist? And in fact, it does. There is a duration class in the java.time library. Right? Let me go ahead and import this. That duration is a more abstract idea of, it could be 5 seconds, it could be 5 years, right? There is no fixed unit of a duration. It's just an abstract concept. We don't have to worry about those details. In fact, if we were to take a look inside this, we can see that they actually modeled this by using a long for a number of seconds. So a 64-bit signed integer, so you can represent a very, very long time, a very long duration. But they're also keeping track of nanoseconds. So that they can have very, very small precision as far as time goes. All right, so let me go back over to my Isotope class here. I can no longer use this year because I've said that I want to redesign this as a duration. And by the way, before we go any further, we also need to update our documentation here. This decays this isotope by, this method decays this isotope by simulating the amount of time given as a duration, not as years, and returns the amount that it has decayed. Now that's way more general, because now I can create a duration outside the class and say that it's 5 years or 3 seconds, right? There are some isotopes that decay in a matter of nanoseconds, so now I have support for that. I do need, since I have this this function or this formula in terms of years, I do need to take this duration and ultimately convert it to years. So d dot get. Let's see. I think well, we could do it as a long, but let's go ahead and go like days. I think, or dot as is it dot. Let's see, 2 days. That's it. We need to convert it to days, and then I'll go ahead and divide that by 365.25. Right? Putting all of that in, of course, the numerator there. Now 2 days is actually returning a long, an integer. So we do have a potential truncation issue here. However, since I'm using 0.25, essentially I don't have to explicitly typecast this. It should be a double. Okay. Now let me go over here to this demo class here, and instead of providing a decay, I'm now going to provide this a duration, more abstract duration. I do want that to represent a year, so let me go ahead and call it year. 1 year of decay. Sorry, gotta spell it right. There we go. All right, and let's see. Yeah, it hasn't been initialized yet. So what we have to do is how do we create instances of classes? Well, generally we call a constructor. Except that there is a constructor in this class. In fact, if it will tell us add arguments to this so that we can provide the number of seconds and the number of days. And of course, that would require me doing a bunch of math myself outside of this class. 365.25 days in a year, 24 hours in a day, 60 seconds or 60 minutes in an hour, and 60 seconds in a minute, right? It's not even going to let me do that, though. Let's go ahead and find out why. Let's go ahead and go into that class and look for those for that constructor. Oop, there is no construct. So duration long. There it is. So there's the duration. It takes the number of seconds and the number of nanoseconds. But as you can see right here, it's not compiling outside because it's been made private. Now this is a design decision that they decided to go with. They decided to close off the outside world by making all of their constructors private. In fact, I think that this is the only constructor. Instead, the way that you interact with this class and create instances of this class is through basically what are called sometimes they're called factory methods that allow you to, all right, give me the amount of time that you want, the duration that you want, and also tell me what units you're in, so that you can say, I want 5 seconds or I want 1 year, right? And so what they've got is a series of static methods to do this for you. Static methods, remember, belong to the class, and so you use the class name, dot, and then all these static methods are called of days. If you just want, I just want 365 days. However, it's long, so I wouldn't be able to do 365.25 to account for leap years, or hours, or milliseconds, or minutes. There is no of years here. That's okay because we've got this general of right here. The amount of time that I want is 1 year, and then what I have to do is I have to use this other class called chrono units dot years. There we go. And I need to import that now. It should be chrono units. Let's see, of temporal units, sorry. I thought it was temporal unit. I think it's chrono. I thought I had it. It's chrono unit, sorry. Chrono unit dot years. All right. So pluralization over here, no pluralization over here. Actually, I should have known that because it is best practice to not pluralize your classes. For example, if you're going to make a person class for your project, right? Person, it's a blueprint. Now you can create a list of person instances, and you could call that people, or you could call that persons, right? But you don't call the class itself persons. It's a blueprint. You don't call a blueprint for a house, this is houses, right? That doesn't make any sense. Instead, it's a blueprint for creating a house, or creating 2 houses or 3 houses. Each unit, each instance is a house. A collection of them, you can call that houses, but you don't pluralize the blueprint for that house, right? So that's why I didn't say isotopes. It would have been very wrong because it's not isotopes, it's one isotope. And right here, the class itself is chrono units rather than chrono units, but it does pluralize the years over here, okay? Now let's see that we didn't break anything. Oops. Unit must not have been, oh, we've got some unsupported temporal type exception. Unit must not have an estimated duration. Oh, darn it. We're not going to be able to do this then. All right. Let me pause here for a second. Actually, no, I'm not going to be able to pause with OBS. Sorry. But you get the ideas. I'm going to go ahead and fix this later on. This is not going to affect our actual design here, but you get the idea. That you can go ahead and provide a duration instead. Right? We could go duration. There should be an easier way to do this. Must not have an estimated duration, probably because years is an estimate, like 365.25. All right. For now, though, let me just go ahead and of year. Let's go ahead and change this. I'm going to make a note to do fix. We'll go ahead and go with a duration dot of, and we'll just go with an estimate here of 365 days so that we can actually move on. All right, and this should work. Yep, we get the same amount because our scale here is 30 years. That 0.25 is not going to make a huge amount of difference on our values here. But of course, if I were doing this as a scientific application, I would definitely want that 0.25 right there, right? So we can actually probably do something like years dot or year dot add to dot add. Nope. We'd have to do something else. All right, I'm gonna move on. I'll come back to this maybe on Piazza. Okay. But you see the idea here that if you're going to design a class, use an off-the-shelf solution. That if you want to, this class itself, if you did it right, if you wanted to design and roll your own, you've got several thousand lines of code here, of code and documentation, to several hundred or 1,500 lines of code here to actually write. Plus the ancillary classes of those chrono units, temporal units, and a bunch of other things. Right? So don't reinvent the wheel. If there's an off-the-shelf solution already there, then use it. Okay. All right. Now what I want to do is I want to continue to redesign and refactor this class. Remember that the set mass that we didn't want. In general, you want to prefer immutable objects. That's why duration is also designed to be immutable. All the time library stuff is immutable. Strings are immutable, etc., etc. So let's go ahead and get rid of this setter right now. Okay. Now there is a problem with the setter that if I want to, I can't reset that value, right? That I can't now say that I do have a mutator here that it'll decay down to 4.99 grams, right? But what if I wanted to, create a new one, and I'll start out with 1 kilogram here, 1,000 grams. Oops, I made a B here, Strontium 90B. Or I've got another sample basically. This is sample B. I've got sample A and sample B over here, and I'll just call it sample B. Right? And I wanted to change it, so I didn't mean that there was a whole kilogram of this stuff. There's only actually 5 grams of this stuff, or something like that. Sample B. I really do want to change that. Right? So dot set, and I can't do that anymore because I've taken away that setter. Right? That means that okay, well, I'm gonna have to, all right, change that to 5 grams there. Right? But you see that there's a lot of repeated code here, right? That every time I want a new sample, or every time I want to model a new sample, I'm going to have to call a constructor based on everything here, right? I'm going to have to provide 38 again, the name, the symbol, the half-life. All of that is repeated code right there. And all I'm doing is changing the amount over here. Okay? So let's go back over here to Isotope and rethink this. First of all, what if I created a constructor where I don't know how much I've got in this sample? I just want the abstract idea of Strontium 90. Let me go ahead and rename this into refactor, rename sample A. Right? Sample A and sample B. What if I wanted the abstract notion of Strontium 90? Right? In other words, I don't actually have a sample of it. I just have the idea of it. Right? And so I'm basically forced to put in 0 here for the idea that I don't have an actual value here. Okay, let's go ahead. But I don't like that idea, right? I don't have a value here. I don't even have 0. It's not an actual sample. So let me go ahead and try to take that off. And you see over here that we're calling this constructor over here where it provides a default value of 0. We designed that last time. But even that's not satisfying because there is no mass here. There's not the idea of a mass. So let me go ahead and change that to a big D double. Right? And now instead of passing in 0, what I can pass in is null. Right? I do have to change the signature of this constructor to allow me to pass in a null value. Null is a good now, there are lots of problems with nulls, and they do present a lot of challenges, null pointer exceptions, mysterious null pointer exceptions that happen everywhere. But it is a good way of expressing something that's generally called tri-valued logic, right? So just take a Boolean, for example. A Boolean can be true, false, but then that's 2 values, a binary valued logic. But you can also have this third way of I don't know, right? It hasn't been set yet, right? If I just create a variable Boolean foo, right, and I don't set it, it's an indeterminate value. In fact, this is a warning. And if I ever try to use that, if foo, then system.out, dot println hello. Right? So if that's true, then I'll output this. But Java won't even let you do that because this is lowercase b Boolean and it has no default value. And so it's warning me right here. In fact, it's telling me that this is an uninitialized variable. This is not even going to compile. I don't know if this is true or false because you never set it. Right? It has a null value right now, but it has an explicit null value rather than just an indeterminate value. I can make a null pointer check on it. If it's null, then output this, right? And it definitely is null. In fact, it's not going to compile here for different reasons because I know that it's the compiler knows that it's null, and so it hasn't been set, right? So that's the idea of trie-valued logic, that you have an actual value. Primitive types have actual values. Lowercase d double always has a default value of 0 in a class, but you do have to initialize it. Lowercase I integer will always have a value. In other words, it'll never be null. But I want my class design here, I do want to allow null because there are some instances in which I would create an isotope without an actual sample. I don't have 5 grams, I don't have 10 grams. It's just the idea of strontium-90. It still has an atomic number, it still has a half-life, etc. It just doesn't have any mass. I don't know what the mass is, right? So I'm going to redesign it so that this is a big D double, and I will end up taking null over here, and of course passing in null over here. It doesn't affect my original values here, that I can still pass in 10. Let's see. Not an integer, but there, 10. That's why it was complaining. But I can still pass this in and pass in an actual sample. But now strontium-90 here, the idea of it has no mass. I wonder what will happen if we try to decay it. Right. So let me go ahead and go down here. We know that this works. We know that everything up to this point works, at least. Dot decay. We'll go ahead and decay it by that year. Right? Let's find out what happens. Now we're going to get that null pointer exception happening at line 57. We try to return this mass from this line right here. We're going to get this mass, and then we try to multiply it over here. Right? So that's a consequence of allowing nulls, that is that we're going to occasionally get a null pointer exception. If you want to, of course, you can go ahead and add some error handling here, that if this dot mass is null, then well, okay, fine, you decayed. I'll make this a no op. Or instead of throwing it, I could throw my own exception. I could throw a new illegal state exception is what I would generally do. You cannot decay a null mass. Right? In which case, when I run this demo over here, I'm not going to get that null pointer exception anymore. I'm going to get my special illegal state exception that you cannot decay a null mass. Or I can make a different design decision. I could say, instead of throwing an exception, I'll just go ahead and return 0. Right? It's a no operation, or a no op for short, an OOP. Right? That you tried to decay something that doesn't exist, okay, that has no effect, and by the way, the amount that it decayed was 0. Right? And now no null pointer exception, but also no, it doesn't have any effect basically. That particular input or that input for this particular instance will end up being a no operation. It will end up not mutating it. Okay. Well, again, the problem here is that I still have to repeat a lot of code over here. So here's a common and very useful pattern that you can follow. Instead of forcing them to provide all 4 of these things at the same time, what I can do is I can create a copy constructor. Now you're not going to be able to. I don't believe that you're going to be able to auto-generate this, but here's what it looks like: public isotope, and I will take another isotope. Right? That I'll call it that for now. I'm going to go ahead and change that later on. But what I want to do is I want to make a copy of this isotope so that I can change its mass. I'm going to take that isotope and copy these four parts of it into it. Right? So this dot is equal to that dot atomic number, that element name, and that half-life. Right? And then of course you can take care of the mass. This dot mass is equal to null. Right? We don't like to repeat ourselves. DRY, don't repeat yourself principle. So we solved that last time by making this constructor up here call this constructor over here. Let's do the same thing, right? So instead of making all of these these assignments manually, I'm going to go ahead and call this constructor on that atomic number, that element name, that element symbol, and then that half-life. And since it's already taking care of that null value for me in that other constructor, I'll go ahead and call this constructor right here, and it'll take care of that null for me, and I don't have to worry about that. Right? That's a copy constructor. What I want, so let me go ahead and go over here, strong team 90, and I'll just simply pass in the sample that I have. Right? And I don't have to repeat that code there. Right? And it'll work as before. Right? It has, again, the strong team 90 decay has no effect because we're just simply returning 0. But I now have a much simpler code over here because I gave myself a copy constructor. Now, what if I want a copy constructor that also changes? I do want a sample B of strong TM90, but I want 5 grams or 2.5 grams. Let's just make it. Let's say 42.5 grams, just to make it completely different. Obviously, that constructor that takes one isotope and a double does not exist. Okay, let's give it to ourselves. If it doesn't exist, there's nothing stopping me from creating it and designing it. These are my classes, right? So I'll create another copy constructor that takes one isotope and the amount that that new isotope should have. Double mass, right? And here I've chosen to make this a small d double because if you're calling this copy constructor and providing me a mass, then you need to give me mass, right? If not, then you call this constructor over here, right? By adding more and more constructors, I'm making this a more flexible class. This is in contrast to, say, the duration class that doesn't have any constructors, and instead it has a whole list of different static methods that you can use to create a duration based on seconds or based on days or based on milliseconds, right? The more ways that you're giving somebody a way to create something, the more flexible your class is, and generally the better designed. So I'm going to make this more flexible by allowing you to either create, just a copy with no mass, or a copy with a mass. Right? And now over here, I have my sample B, which has 42.5 grams, and I'll go ahead and decay that one now. In 1 year, I should have, I don't know, a double decayed amount is equal to this. And I'm going to go ahead and print that out because it should actually decay by some amount, right? Just to show that it actually works. So it looks like it decayed 1 gram in that 1 year on sample B. Okay, that's a copy constructor. Very, very, very useful pattern to use, especially on your project going forward. Right? All right. Another piece that we saw that we saw in the duration class. Let me go back to the duration class, and we'll take some design tips from that class. Let's go ahead and take a look at the seconds and the nanoseconds again here. And you probably saw this in your lab last week and again in this week. They've got this additional keyword over here. Not only did they make this private long seconds or private int nanoseconds, but we've also got this final keyword here. In Java, the final keyword is used to make a constant. A final variable, once you set it, you can never reset it. So let me go ahead and show you what I mean over here in demo. And let's go ahead and create final int value is equal to 42. Okay. Once I've created that, later on, I can't reset it. Try to set it to 43, and that will be a compiler error. The final local variable cannot be assigned. It must be blank. Blah blah blah. Basically, it's you created this final variable, meaning that once you set it, you can no longer change it. Examples of why you would want to do this is I've got math.py. Right? What if I tried to set that equal? That's a public variable. What if I tried to set that equal to 3? 0.15 instead of 0.14. It's not going to let me do that because it's going to be final. The final field cannot be assigned, right? That's the idea behind the final keyword. You can add that to your class if you really want, if you want to just make doubly sure that those will never change, right? But now that has a consequence. Remember, we decided to design our class so that it was mutable through this decay method. So in this particular instance, atomic number will never change, right? You're not going to take a sample of strontium and turn it into a sample of uranium. You should just create a brand new instance to do something like that. So I do have to meet halfway here. This at least cannot be final, right? We could redesign this class even further so that the decay function, the method, instead of returning the amount that it decayed and changing the class, you could return a new copy of the class that has been decayed that much. What would that look like? So let me go ahead and I will keep this so that when I post it, you'll have that still there. But what we could do is we could make this into a final variable, right? Just like strings are fine, and this is 100% thread safe. This is 100% immutable. You cannot change this. So what would the decay look like? Well, instead of returning a double, we would return a new isotope, right? Instance. If this mass is 0, then I can return null, right? Instead of 0, and now I need to return an actual instance of a class. And since it's invalid, I'll just go ahead and return null as a value here. Otherwise, there's the remaining amount, there's the decayed amount. And what I can do now, instead of resetting this mass, which I can't do anymore because it's final, I can create a new instance of it and return that new instance. And because I've already created my copy constructors, I can just pass in this and however much is remaining. There. Now I'm returning a new isotope. Over here, of course, I would have to make a proper changes. Isotope. This would have no effect anymore because we're not capturing the return value. But the decayed sample, right? Now it's no longer just I've got sample B, I decay it by a year, and it gives me a new isotope with a decayed sample. Let's go ahead and take a look at what that looks like. If I try to print out the isotope, I get this weird thing down here, right? What is that weird thing? That is the class name followed by the Java virtual machine memory address at which it's stored. That's really weird. What I wanted is I wanted a human readable way of looking at this, right? And there is a way that you can do this pretty easy. All you have to do is, now here's the trick I was talking about last week, to generate code. You can go up to source, generate toString, right? And I'll go ahead and have it I'll output all of the fields, right? I'll generate this. Let's see what it looks like over here now. We'll come back to that code here in a second. But now instead of printing out that mysterious virtual machine memory address, now I've got this stuff down here, right? The isotope, atomic number 38, strontium, element number, etc., etc. Now let's go back and make that a little bit more readable, because this was just auto-generated code, so it's just going to print everything out like in this default manner, this default formatting. So what I'm going to do is I'm going to go ahead and change this so that we output the element name concatenated with a hyphen, and then the let's see, 90 would have been oh, I guess we're not capturing that. Okay, strontium, nowhere did we provide 90. Okay, nope. I just put that into my variable name over here. Strontium, we'll put then its atomic number, so plus this dot atomic number there, and then plus a space plus a number of grams, this dot mass, and then we'll concatenate that with a label that says G, right, for grams. And let's see what that looks like over here now. And we've got strontium 38, That should actually be 90. I don't like that. Let's go ahead and put that in parentheses there instead. And now we've got 41 grams remaining of the original 52 because it has been, this is the decayed sample that we're printing out here. If you want to, this is a perfect opportunity to use a printf style formatting. System.out.printf, println here, or printf, excuse me. We'll go ahead and print the string, which is the atomic or the element name, and then in parentheses I'll go ahead and put in the number, which is a %d, and this dot atomic number, and then that space, and then percent, and just 2 decimals of accuracy is fine here, 2 grams, right? And this dot mass. Okay. What does that look like? Well, it's not going to compile here because I'm using system.out. What I want is I want to format this into a string. If you're coming from a C background, you have printf, you have fprintf, which can print to a file. You also have sprintf, which prints to a string. You can have you have the exact same functionality here in Java using string.format. It's not called printf, unfortunately. It should be, but it's called string.format here. And I will return that as a string. When I get that over here, then I get strontium 38 now in parentheses, 41.49 grams instead of that really long number. Okay. That is the toString method. And just like constructors, if you don't provide a constructor, a no argument default constructor is provided for you. And the default toString method would print the class name followed by the Java virtual machine address of that instance. But if you, of course, you can always override that method to do whatever you want. And this is something called an annotation. We might talk about that later. It's not absolutely necessary. It was auto-generated by Eclipse. It's not hurting anything to leave it, though. Okay. ToString methods do not generally need to be documented because they're part of the class. Really, the only method in here that needs to be documented is this decay right here. All the constructors, getters, setters, those are trivial methods that don't need documentation as far as your project is concerned. In the real world, of course, I would probably do this, but I would also write a script or modify my IDE like Eclipse here to auto-generate that stuff for me so I didn't have to write it. Right? I will leave all of those in there for now. Okay. All right. Now what we're going to do is we're going to switch gears here a little bit and cover everything up to this point has basically been a practical demonstration, a practical tutorial. What I want to do now is go back and look at everything that we just did, but I want to start codifying these concepts as OOP concepts. Okay? All right, so let's go ahead and go over to the notes here. Let's see where... Here we go. Here we go. All right, so... object-oriented programming. There we go. Let me give myself some more room here so that it always jumps up. Okay. There we go. All right, so to start out with, here's a little bit of a history, I guess, if you want. Or at least this is my take on the history of object-oriented programming. Computers started out, very low level. Computers, the very first computers, vacuum tube computers, punch card computers, basically forced you to program in binary. So you had to take an idea of an algorithm, say computing a square root or whatever, and you had to formalize that on a piece of paper, graph paper, or up on a blackboard or something like that. But ultimately, at the end of the day, what you had to do is you had to translate it into a bunch of zeros and ones that the machine actually understood. And so you actually had to manually punch the punch card, translate your program. Basically, a human was acting as a compiler. Very, very tedious work, right? That's why the entire process was slow. And if you had a bug or made a 0 instead of a 1, that entire program, you'd have to go through it and find your error. Then along comes higher level programming languages like assembly, right? And so with binary, of course, it's forcing you to strictly think in terms of zeros and ones. At least with assembly, you have some close to English words to work with. Assembly code looks something like take the value or load up the value 5 into register 1. Load up the value 10 into register 2. Take the value register 1 and take the value of register 2, add them together, and place the result into register 3. If the result in register 3 is greater than that stored in register 4, then jump to memory location 5, right? It's still very, very tedious. It still forces you to think like a computer. It still forces you to think in this procedural way. Then along comes a higher level programming language like C or C++, etc. These higher level programming languages in the late or even before that, Fortran, where now you don't have to think in lower level terms. Now you can actually have something that more resembles English. Int A is equal to 5. Place the value 5 into A. It's still kind of machine speak, but at least it's a little bit closer to English. Object-oriented programming comes along and says, look, I want to be able to program by reasoning about entities. I want to design a program where I've got the idea of an isotope. And then I can interact with that isotope and say, you decay yourself by 5 years, or you decay yourself by 5 seconds, right? And then I can take this object and I can interact with another object, a duration or something. And now it's much more high level because now I am thinking in terms of entities. I'm thinking in terms of objects. And so object-oriented programming can be seen as this evolution of programming languages. At least that's my take on it. Right? Other people who are very much in tune with, say, functional style would say that it's a step backwards, or you're doing it wrong, or whatever. Don't worry about the little spats online of, well, that's not really object-oriented programming, or object-oriented programming sucks. Like Linus Torvalds would say that OOP is the worst thing to ever happen to, or C++ is the worst thing to ever happen to C and stuff like that. Don't worry about it. There are legitimate gripes on any language paradigm. There are legitimate gripes on any language that you can come up with. Because we're always going to be fighting that battle of human versus machine. To actually program these machines, we still have to think like machines in some manner. We're still not to the Star Trek level where we could just say the computer, not even Alexa is very good at following your instructions. We're still not to the level where you can tell a computer do this, and it completely understands what your intent was, right? So object-oriented programming is just one step towards that Star Trek utopia where we have computers that just understand the best programming language, natural language. For most of us, that'll be English, but of course you could, program in any natural language: Chinese, Japanese, Korean, whatever you speak. That's your ideal programming language. You just want to talk to the computer and tell it exactly what you want and what you want it to do. Right? A little bit of history. I think object-oriented programming started with not ADA, but Scheme. That's functional. But it's quite old. It's from the early 70s, I believe. Smalltalk is given credit for being one of the first object-oriented programming languages. Of course, most object-oriented programming languages are nothing more than existing languages that have had object-oriented aspects slapped onto them later on. C++ came out of C++. Well, it's the next C. Originally, it was called C with classes, right? So, and really, it wasn't even its own language. All it was a transpiler that took your class code and your object-oriented programming code and simply translated it to C and then used a C compiler. You have C, Objective-C coming out of that. You have C# coming out of that. You have Java being developed in the mid-90s as object-oriented programming first. So there's a little bit of the history. Don't worry about it, right? But there are 4 pillars plus 1, and we'll cover the plus 1 here first, because you can't have object-oriented programming without talking about objects, right? So formally, an object is a general entity characterized by 3 things. And to save some typing here and to make this a little bit tighter, I'm just going to go ahead and cut and paste from my notes here. Identity, state, and behavior. The identity is simply an aspect of the object that distinguishes itself from all other instances. Now, for the most part, that's going to be where it's stored in memory. If you've got an object stored in memory address 1234, and you've got an object stored in memory address 5678, then that could be your identity. These two objects are different. In fact, that's what the default in Java is. That's why equals equals works for objects, because you're asking, is this object's memory address, is it the same one as this? Well, then they're the same thing. But of course, you can define identity differently. You can say that, well, this string is equal to this string if they can have the same contents and their casing matches. HELLO and HELLO, all lowercase, oh, that's the same object, right? And even though they're two different instances stored in different memory locations, for all intents and purposes, their state is the same, therefore they are the same. Right? And that's a way that you can do that. You can do that you can do that easily over here in Eclipse by going up to source, generate hashcode and equals. Hashcode is generally, you have to do that along with equals in order for collections to work correctly. Let me show you what it generates by default here, right? So first of all, it checks to see, are they the same objects in memory? Well, then we're done, right? Then they're definitely the same object. Otherwise, it starts checking things. Are they the same type of class? If they're not the same class, then they can't be the same type of object. Return that. If that object is null and this object is not null, then they can't be the same thing, so return false. Otherwise, it goes through, and if the atomic number is the same as that atomic number, the element name is the same as that element name, the element symbol is the same as that element symbol, etc., 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 then it returns true if all those things. If any one of those things is different, it ends up returning false, 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 false. Otherwise, it returns true. Now, that's important if you're trying to define identity as having the same state. That this isotope sample is the same as this isotope sample if all 5 of those pieces of its state match. Otherwise, by default, all 5 of these pieces of state could match, and it still would be unequal. They would not be the same thing because they're at different memory locations, right? It all depends on what you mean by identity. But that's the first aspect of an object. The second aspect of an object is its actual state. It's a collection of properties or elements or attributes, data, field. We call these, in object-oriented programming, we generally call these member variables. And in our isotope over here, these 5 values are all member variables. If you had a static variable, public static foo, right, equals, let's say that it's an integer, foo is equal to 42. That's not a member variable because it's static. It belongs to the class. It belongs to the blueprint itself. These are all member variables because they're non-static. They belong to instances of the class. Over here, isotope is the class. If I wanted to access that foo variable, isotope.foo, right, then set it equal to 43 or something like that. I think you can do that. Did I make it? Yeah, I made it public. I made it mutable. It's not final. And so I can change that, right? It belongs to the class. There's only one foo variable. It's basically a global. And it's a mutable global here, which is bad. Don't do that, right? But it belongs to the blueprint. It belongs to the class. Each one of these is a member variable because it belongs to instances of the class. Sample A does not have the same state. It has 10 kilograms instead as sample B, which has 42.5 kilograms. There are different copies of those 5 variables in memory, and so it all depends on what you mean by identity. But we call these member variables. Let's check the time here. Make sure that. Yep. Okay. We'll go ahead and cut it after about an hour here. But otherwise, since it's a recording, otherwise the third part is that you have behavior. Now we kind of have this idea, these first 2 ideas in most programming languages. Like C is not an object-oriented programming language. Similar, MATLAB is not an object-oriented programming language per se, but it does have support for structs. Structs or structures, they have state. You can take those 5 pieces of data and you can encapsulate it into one logical unit called a structure. But you don't have this third value, this third idea over here of having behavior along with it. That's the functionality of the object, or what it does, or what services it provides. Over here, our isotope, well, it has a bunch of getters and setters. That qualifies technically, but they're kind of trivial. The only non-trivial thing that we did over here was the decay method, right? That's its behavior. How does this isotope actually decay? Or what is the behavior of this isotope? Well, an isotope decays over time. That's its behavior. That's a method. In a programming language like C, we would have to put this decay method outside the class, violating encapsulation, okay? So an object has these three things. Generally, communication is done through what's called message sending. Right. There you go. That one object calls another object's methods by sending it a message. Decay yourself by 1 year. Decay yourself by 2 years, right? You simply invoke a method on that object, and that object determines which code is run. That this code over here, now that you sent a signal to this isotope to decay, okay, well that means that I'm going to execute this code inside of myself, right? I'm the object now. Communication is facilitated through what's called an interface. An interface is simply, in Java, an interface can be thought of as the publicly available methods. If I made this into a private method, right, that's not part of the interface anymore. Sample A dot decay is no longer part of its interface. All these other methods are part of its interface. That's how you can interface with the object. But now it's no longer, now that decay method is no longer part of its interface. So basically, an interface is its publicly available methods. Let me go ahead and restore that to public. Okay. Objects are constructed instead of assigned, and we've already gone over this, so I won't. I'll just go ahead and go with the short version of this. Objects are constructed instead of assigned. In Java, by default, the no argument to constructor is provided like a lawyer. If you cannot afford one, one will be provided for you. If you cannot afford a constructor, a no argument default constructor is provided, and it assigns null or zero values based on an object state. In Java, if you define a constructor, that no argument default constructor goes away. But of course, you can go ahead and restore it. We looked at, in our demonstration, in our tutorial, we looked at copy constructors, partial constructors that only took part of the state. It took the first 4 elements instead of the mass, because we left that off to be null because we didn't. It was just the concept of an isotope rather than a sample of an isotope. Objects are designed. The general approach is that semantics dictate design. In other words, the handout here tells me what an isotope is. An isotope is an atomic number, an element name, etc., etc. That's pretty straightforward there, right? Those 5 things should be part of the state of the object. You just think about a person object. What is a person? Well, a name, but a first name and a last name, and maybe a middle name. All 3 of those things should be as one. A person also has an address. Okay, well, what's an address? It's a city, state, zip, country, and of course the street number, right? 1, 2, 3, 4, A Street. Wait, that sounds like 5 things. What's that? That's a huge red flag sitting right in front of my face. What should I be doing with those things? I should be making an address class. So what is the interaction between a person class and an address class, right? Instead of having those 5 things as part of a person, those don't define a person. Those define an address. An address defines partially defines a person, right? That's called composition, right? Generally, you want to prefer it. I'll define that in a second here. But basically, the approach that I just took of describing that process is that you break a real-world object down into smaller and smaller parts until it's simple enough that you first name, well, that's a string. Last name, that's a string. Address, oh, okay, that's a class, so let's go ahead and define that over here. All right, now I've got an address. I've got a birth date. Right? A birth date? Gee, I wonder, is that already done for me? Yes, local date, pull that off the shelf and use it, right? A published date like you'll see in your lab this week. So you break it down into until it's simple enough to just represent it directly, like a number or a string, or an object, off-the-shelf object already exists, just use it, right? Don't reinvent the wheel. Generally, what I said is that you prefer composition. That's when one object is composed of another object. Let me fix that indentation. That's when you relate one object to another. Alternatively, inheritance, we'll talk about that probably next week. But we were using composition all over here, right? This is composed of a string, which is a class, right? Big S here. That is a string class. In fact, it's 3,500 lines of code here, or locks, right? That is a double is a class. Not as big, probably. Only 1,000 lines of code. But an isotope is composed of these 5 things, right? If I were to create a person class, and this is what I'm doing in the other section, if I were to create a person class and an address class, a person would be composed of an address. A person would not simply have a street, city, state, zip, etc. The person would be composed of that other class. In fact, I can show you what that looks like. Here is the code from the other section. Here's my person class, right? They're composed. Also, they have a set of emails, right? That is a collection of strings. They've got an address and a date of birth. That address has those 5 things, right? And so you break an object down until until it's a different object, like conceptually a different object, like an address or an email or something like that. And emails in this case are just being represented as strings. Okay. You do want you want to break things apart because you want to avoid what's called the God anti-pattern. So an anti-pattern is simply just a bad pattern, a bad habit to get into. It's related to something called code smells. So code smells are something that stinks, kind of stinks. That you're looking at your code and there's that code kind of there's a smell to it. It's not necessarily a bad smell. Maybe it's an okay smell, or maybe it's not that bad. But it all relates to something called anti-patterns, where it's a bad habit to get into. It's common, right? Bad habits are common, but it's not a good idea to get into it. The God anti-pattern refers to where you basically throw everything into one class. That class is God. It sees everything. It does everything. It is everything. And you don't want that. You want to break things apart into other classes, just like you don't want to put everything into the main in a C programming language, right? Or a scripting language. You don't want, you want to break it apart into functions, right? This is a repeatable piece. This is one logical unit. I'll move that unit over into a separate function. And then you have function call, function call, function. So that you don't have just one big giant glob of code, right? That's the God anti-pattern. As I said before, we've got 4 pillars plus 1. The plus 1 here is objects. So what are the 4 pillars? We're going to save inheritance and polymorphism to next week, but we have more than enough here to talk about abstraction and encapsulation. Actually, we might have to save these for next week, but basically, let me go ahead and identify them really quick. Abstraction and encapsulation. All right. So abstraction is basically implementation hiding, right? The motivation here is, and we'll retread this next week because we do have a special lecture on Thursday on technical writing. But basically, the question that I usually pose is that square root function in the math library, how does it work? Does it do a Taylor series? Does it do the Babylonian method? Does it do some other numerical interpolation method that has very special convergent properties, blah, 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 blah? Who cares, right? The whole point of having a function, a square root function, is that I simply call it. You pull up your calculator. Have you ever wondered how those buttons work? No, who cares? It just gives you the answer, right? It's implementation hiding, right? It means that you don't have to worry about the details of the implementation. That it's like procedural abstraction, a function. It's just a black box. You put input in it and you get output from it, right? You need not worry about how an object, or in this class, is implemented, or how it works, right? Its behavior. You need not worry about the details of. There we go. You need not worry about the details of how an object or class is implemented or how it works. Its behavior. You simply use it. Right? So that duration class, we ripped it open because we were kind of interested, but how did it actually represent a duration? Well, it had a long value that represented the number of seconds. It had an int value that represented the number of nanoseconds, right? We didn't need to know that. We didn't care. In our code, we simply just had to use it, right? That we wanted to create a duration that of days, 365 days. We simply interacted with it through its interface, right? You simply use it using its publicly available interface. Right? We don't have to worry about that kind of stuff, right? Finally, how is time represented? Right? How is a duration represented? Right? Or even more basic, how is a string represented? Right? There are lots of ways that you can represent strings. You can represent it as a null terminated character array, like C. You can represent it as a length prepended string. So we've got our string, our characters, not necessarily an array, and there are 5 characters in HELLO. We'll go ahead and append that metadata to the beginning of it, all right? Another detail would be, well, does it support Unicode or just plain old ASCII? Who cares, right? It's just a string. You just start using it. You just start using the plus operator to concatenate things, right? Encapsulation is 3 things, right? This is my definition of encapsulation. You'll find that in a lot of authors kind of conflate abstraction and encapsulation. I tend to look at it as like an MC Escher drawing. If you're familiar with that, with the one hand drawing the other hand, but that hand is also drawing the first hand. They kind of act like that. They're the yin and the yang. Their abstraction and encapsulation go hand in hand, basically. Without one, you really don't have the other, because without encapsulation, you can't group pieces of data together to form an abstraction. Without abstraction, you can't interact with the class that you created. Right? So encapsulation usually is comprised of 3 things. Right? 1, the grouping of data into one logical unit. 2, the protection of data from the outside world. And 3, the grouping of methods or behavior that act on that data. Okay? So we've seen this now with our tutorial. 1, the grouping of data into one logical unit. By creating an isotope class, giving it member variables, we've collected those 5 things into one logical unit, an isotope. The protection of that data from the outside world. We made them all private, we made them all final, so that it's an immutable class, right? It can't be changed. We allow the outside world access to those variables, but we have no setters here. We're protecting it, right? The setter that we did have, that I unfortunately deleted, well, we allowed it to be mutable, but we protected that data from the outside world in that we did not allow somebody to set the mask to negative values, right? We were protecting that data. The grouping of methods or behavior that act on that data, well, that's where the decay function comes in. The rest of the functions, the rest of the methods also act on that data, but this one is the one that does it in a non-trivial way. That you interact with this object by calling the decay method, decay yourself by 1 year. It takes care of that, right? If I were to put this function outside the class, say in a utility class or something like that, public static isotope, basically what I would have to do is take one isotope, that, and the duration there, and then I would have to rip it open. I could no longer talk about this isotope. I would have to talk about that isotope. I would have to call its getMass.getMass, right? I would have to do that all over the place here. That's why, oops. That.getMass. Oh, okay, because there would be no pointer because that does not return. It returns a small d double. That's why. And then that.getHalfLife, and then return that copy. Right? It's the same basic code, but it's a terrible design because I have ripped open the object and I've spilled its guts all over the place. Now this decay method is completely outside of the class, right? That's a violation of good encapsulation. The whole reason that you create classes is so that you can group both the data and the methods that act on that data into one logical unit, right? Coming from maybe a programming language like C where you only have structs, you have weak encapsulation. You only have the first one where you can group pieces of data into one structure. You can't protect your data, and you certainly can't group methods easily, I should say, into a structure. You do have function pointers, and that's how early C++ worked, but it's a terrible way of doing things. Okay? We'll retread this slightly next week when we come back to this, to object-oriented programming, but we'll mostly focus from here on out on inheritance and polymorphism. Right? I'll see you on Thursday, hopefully in class.